Okay, top minus bottom from 0 to 1. Now, I don't know if I actually ask you to do the integral or set up the integral, but this is easy enough integral to do. X to the 1/2 would be x to the 3/2 times 2/3 minus x cubed over 3 from 0 to 1. This would be 2/3 minus 1/3. The zeros give you 0. You get 1/3 as the area. The area between those two is exactly 1/3 square units. All right. Now, the next one I say, find the integral that gives the mass of the lamina. The mass, since we have a constant density in all the laminas, all the problems we're talking about in this chapter, density is a constant. So we simply have a density function. Bless you. Bless you. Bless you. Yes. That would be the mass.
So the f of
Why
x
is
minus...
it 1/3?
Why is what?
1/3.
Because 2/3 minus 1/3 is 1/3.
Yeah, but 0.
And the zeros give you 0.
Oh, we put, okay, got it.
Got it? Okay. The mass would be the density times the area.
What's P?
Rho, this is rho. This is a density function. Think of this as, for example, grams per square centimeter. The area gives you square centimeters. This gives you grams per square centimeter.
Unit kind of?
Yes, yeah.
So you always do f of x minus
Kind of like
g of x.
Yeah, top minus bottom. It's always top minus bottom, whatever top is.
Well, there's no top for this one.
Yeah, there is a top. Square root of x is top here.
Oh, top, okay.
Yeah, that's top. Okay? All right, there's the mass. Find the integral that gives the moment from the x-axis. Now, the difference between the moment and the mass is that a moment is a mass times a distance. And what we said we would do from the x-axis, you take this little rectangle in here, and what we said we would do from the x-axis is take the midpoint. So the distance we're looking at is this distance here. We're taking this midpoint, okay, right here. So this distance, what is that equal to? Well, it's the average of the two functions. So what's the moment from the x-axis? It's a density function. 0 to 1, top minus bottom. That doesn't change, except now we have a distance times a mass, and the distance is going to be that point right in between the two. It's going to be equal to x squared plus the square root of x over 2. Okay?
Is that like a formula or something?
Yes, it is a formula.
Well, that's like an type for an average, right?
Yes. Actually, Nick asked about the formulas. Let's go back to the area. The area formula is top minus bottom, okay? Depends on what top is. I'm going to call f of x top minus bottom. That's the area formula. Mass formula is a density times the area. Moment from the x-axis, density, top minus bottom again. But now we've got the sum divided by 2. Okay, that's the moment from the x-axis. This is a mass times a distance. If you look at this, what we've got is a density function. We've got top minus bottom. That's the length of this rectangle. We got a delta x from here. That's the width of the rectangle. We got an area of a rectangle times the density, which gives us a mass of a rectangle, times the distance. That's what this is. Moment from the y-axis. Still f of x minus g of x. But now the distance, instead of going from here to here, the distance from the y-axis is this distance, which is just x. Okay? And in this particular function, the moment from the y-axis is equal to the density, the integral from 0 to 1, square root of x minus x squared, times x dx. Okay. And number 5 is a gift from me to you. X bar is equal to the moment from the y-axis divided by the mass. So you really
Is that
don't.
definitely going to be on the exam now?
It may be. It may be. I can't guarantee it. It may be.
Or the Y bar.
Y bar is the moment from the x-axis over the mass. Yeah. One of those two.
So Y bar is what?
MX over mass.
Yep.
Oh.
Moment.
Yep. Okay. Okay, that's the first section. Any questions on that?
When, for the MY, are we just going to have to give that for the X? You see how you put X there? It's not going to
Yeah.
have to be a number or anything?
No, it's always x.
Okay.
Okay. All right, 6. Oh, Nick.
For the exam, would you want us, like, for 1 through 4 there, would you actually want us to solve them, or?
I don't think so. I think I have just like what I have
You
here.
want them just kind of set up like?
Yeah,
that?
I believe that's exactly what I have you do.
Okay.
So all you did was write the MY. Is it pretty much components? Is that what it is? Components of mass? Is that what they are?
I don't like the word component in that context. You use components in like vector context, but it's not really a component here.
Oh, okay.
It makes up the mass, that's true. Yeah, I guess we could in that more general sense of the word component. What's that mass equal to? It's equal to an area times a density function. If you call those
the different over the X and over the Y.
yes, and those are the two, yes. I would agree with that.
That's not the centroid, those two? No.
Yes, it is. This is the centroid. X bar, Y bar would be the centroid of this lamina. It's exactly what those are. That's a centroid. It's the point at which that lamina would be balanced on the head of a pin. That is called the centroid. Okay?
Centroid when density is 1.
Say that again.
Centroid when density is 1.
When density is equal to 1,
Yeah. Like we don't have A.
if the density is equal to 1, the centroid is,
That's what it's called, the centroid, right?
yeah. All right. All right, you ready? Okay, let's go on.
4.
Let's do 6 through 11. 6 through 11, we've got a function. Function is y equals x. X equals 4. This would be the point 4. Okay. This is the area in question. Find the integral that gives the volume of solid generated by taking this area about various lines. And the test has the same kind of question. 6, the x-axis. Now, I'm going to do all these with this rectangle.
Just rectangle?
Okay, what's that?
Is it just one rectangle?
Yes, with the same rectangle every time. But I may have a question on the test that asks you what you would use if you were to use the rectangle with respect to y. In other words, would you use disc, washers, or shells, depending on where we're going around. For example, in this one, I'm going to take this around the x-axis. Okay? Now, what method am I going to use as this goes whipping around the x-axis? That's going to be discs. The volume, in this case, is going to be pi, the integral, a to b. I'm going to write the formula out, r squared dx. That's the formula for discs.
X squared is that? Oh,
R squared.
R squared.
Okay, where r is this distance here. That's the formula for discs. I may ask you if in this problem you were to take the rectangles this way with respect to y, use a delta y, what method would you use in that case? Around the x-axis still. That would be shells, okay? Around the x-axis would be shells in that case.
Because it's going sideways.
It's because the rectangle is parallel to the axis about which it's being revolved. That will always be shells. Now, if you were to take this rectangle, the y's, about the y-axis, what would you get in that case? That would be a washer, that's correct. And
But
if,
that's the disk formula, pretty much, right? plus.
Yeah, it's two discs. The difference is two discs.
If you change that to the y-axis, it would be the washer. That's what you just said?
Yes. If I were to take this rectangle around the y-axis, it would be washers.
And you use two discs to clean them.
Yes.
So it'd be the same formula, just minus each other.
Yes, correct. I want to make sure Damien's okay here.
Yeah, I'm good.
So
Okay.
Sorry, for the washer, what way would it be whipping around?
If you were to take this rectangle
Yeah.
around the y-axis, you would get a washer. Here, let me write the formulas for each of these.
I have them here. It's just, there's so many of them.
Isn't it only 3?
There's only 3.
1, 2, 3, 4, 5, 6, 7, 8.
Oh.
Oh, there's that many problems. There's only 3 methods.
3 methods, 2 for each, and then we have the area.
This is over the x-axis you're doing the formulas for?
I'm giving you formulas for discs in general, washers in general, and now shells in general.
Should I give you earlier?
Yeah, I wrote that.
It's just, it's pretty good at practice.
For the shell one,
Mhm.
what would be an example with that up there?
If you were to take this rectangle around the line x equals 4, for example, that would generate a shell. Okay? I'll do some shells. We'll do some. All right, let's do the x-axis first. Take this rectangle around the x-axis, you're going to get a disk. The volume is going to be pi, the integral, 0 to 4, r squared. As you go around the x-axis, what is r equal to? What is r equal to here? It's equal to the height above the x-axis, which is y, which is equal to x. Okay, that's it. All right, check that out.
I don't get the x squared.
Okay, here's the deal.
It's just
When-
part of the formula, yeah.
When this gets whipped around the x-axis and generates a disk, the formula is pi r squared dx, where r is this distance right here.
So is r kind of like what the function is? Kind
It is exactly what it is in this
Exactly.
case.
So, like, yeah,
In this
function.
case, it's what the function is. It's not always that, but in this case it is, because r is the height above the x-axis. And what is the height above the x-axis? That's what y is. That's what the function is. But everything has to be in terms of x. So what you have to do is take the y, it's equal to x, use x squared.
So what would be a case where that wasn't?
Well, we'll do one. We'll get some. We got a whole bunch of examples here. All right, that's number 6. Let's do,
You're just setting it up?
yes, I believe that's all I have you do in the test, too. I'm pretty sure. Just set them up.
Oh, find the integral that gives you the volume.
Yeah, that's exactly how it is. Hey, Trent, I'm looking after you. You know what I mean? I want you to get that 100, you know what I mean? If you have to do the integral, you're subject to error. All right, you ready on this now?
This is a break.
What's that?
We have to do no solving with the homeworks.
I know it. All right, number 7. I'm taking that same area.
You're doing the same rectangle.
Same rectangle.
No, we're just saying,
And now we're going to buy about the y-axis.
Should give us a washer.
This
Shell.
will give us a shell.
So shells like over a straight line kind of.
Shell is when the rectangle you are revolving is parallel to the axis about which it's being revolved. Here's the y-axis. Here's the rectangle. The rectangle is going this way. The rectangle is parallel to the axis. When that's the case, you will generate a shell.
Okay.
Okay? So, shell method gives us 2 pi. X is going to go from 0 to 4. R h dx. Okay? Now, what the heck is r? R is this distance. H is this distance. Okay? R is the distance as the thing is revolving. What is r equal to here? The distance from the y-axis, which is equal to x. What is h? It is this height above the x-axis. What's that height equal to? X again. The height above the x-axis is y, but y is x. So we got x again.
Just 2x, so x.
X squared, yeah.
So
Go ahead.
For, what would be an easy way to remember which is the R and which one is the H?
Height.
Well,
H is always the length of the rectangle, always.
Yeah.
That's probably the easiest way.
Okay, so R is always the opposite.
Yeah, yeah.
I don't really get why
Go
you get
ahead.
x.
Say that again.
I don't get the x part. Like, how do you get?
Just hearing this?
Yeah, I don't get it.
Okay. R is this distance. And what you have to realize is that the distance from the y-axis is x. That's what an x coordinate is. It tells you how far,
Yeah.
okay, that's what it is. And we're using x's, so that's what x is. This distance from the x-axis is y. But we have to be in terms of x, and what's y equal to? X. If this function had been y equals x squared instead of y equals x, you'd use an x squared here. Okay?
What case would it be for minus r? Minus x?
I think it'd be just.
No case.
The H is the wrong side.
Really, no case.
Honestly, the best way is just to
You really wouldn't.
try to like
Number 8, y equals negative 1.
this is what when.
Not one we're going to run across anyways, Melissa. Okay? Number 8, we're going around the line. Y equals negative 1. Okay? Now, when this rectangle gets whipped around that line, what are we going to generate? A washer. Okay? The volume then is equal to the integral pi 0 to 4 big R big R squared minus little r squared. This is what Nick was mentioning a little while ago. Difference of two disk is what we have. 0 to 4. Now what's big R? That's exactly what it is. Big R is equal to this height above the x-axis, which is y, which is x, plus this distance, 1. Minus little r. What's little r? 1. Okay? That's it.
So that's when it washes around the x-axis.
Washers are when you have your rectangle is perpendicular to the axis and there's a gap in between. Let's make sure we're okay.
I'm just curious, how do you get, I'm still confused how to get the X.
This here,
Yeah.
that's equal to what big R is, and what's this big R distance equal to? It's equal to this distance, the height above the x-axis,
Which is X, Y equals X, right?
which is y, which is equal to x, that's where the x comes from, plus this distance of 1.
Now, if it was flipped, you try changing that, you do the opposite, you do X equals Y, right?
If you were to take this with respect to y, go this way,
Yeah.
and use shells, yes, you would have to end up with y's. So you would do just the
So
opposite.
anytime you do it over the Y, anytime you do it perpendicular to the Y, the rectangle,
All right.
I'm gonna
Here's the deal. Your rectangle determines the variable and the method that's used. If you choose this rectangle, which is what I'm doing for every one of these problems, with a little delta x down here, that tells you everything must be in terms of x, and this rectangle determines the method that's used depending on what happens to the rectangle as it's revolved about the line in question. So that rectangle determines everything. It doesn't matter if you're going around an x-axis, y equals negative 1, or the y-axis. You have to be in terms of x, because that's the rectangle.
What I'm saying is it's always perpendicular.
It's not always perpendicular. It could, if this is your rectangle and this is the line, this is perpendicular, and you're either going to get a disc or a washer.
Well, you're gonna use X, that's what I'm saying.
You don't have to. You could use Y's and go this way and use shells.
Oh, okay.
You could use this way and use washers or disc. Depends. Yes.
How do you know which one to use?
You're going to be told. I'm going to tell you in the test, everything is going to be in terms of X.
Whichever your delta is, like if it's delta X, you're using X. If it's delta Y, you're using Y.
Yeah, well, that's it. The rectangle determines everything. Now, which rectangle you're going to use, usually in the homework, they'll tell you which one to use.
Yes.
On the test, I'm going to tell you you're going to use the rectangles with respect to X.
Okay.
So you're going to be told that.
And this practice exam, do we have one like this way?
It's going to be very similar to this in your test. Very similar. All right, that's 8. Number 9, x equals 4. X equals 4 is the line in question. This is our rectangle. As this rectangle gets whipped around the line x equals 4, this one here, what are we going to generate? What is it? Shell. That's the first thing. You got to be able to recognize when you're getting shells, when you're getting discs, and when you're getting washers. Okay? This, about that line, is going to be a shell. Why? Whenever the rectangle is parallel to the axis, it's going to be a shell.
What about disc and washer? What's the difference between those? How do you know which?
A disc is when there's no gap. If this rectangle is going around the x-axis, there's no gap. It's going to be a disc. But if you were to go around the line down here, you got this gap. That gives you a washer.
You could use the washer method every time because your small radius would be 0.
Yeah, you
If
could.
you wanted to just do the same every
Oh yeah.
You
well,
could do
because
that.
It wouldn't, because minus Rx would just be 0.
That's
right?
correct.
So, okay.
Exactly.
That's correct. Okay, let's go around. X equals 4, number 9. We're going to get a shell. The volume is going to be 2 pi. Now, R is this distance. H is this distance. Okay. What is R going to be? Now, this is where it gets tricky. This R is equal to what?
4 minus X.
That's exactly what it is. It's 4 minus the distance from the y-axis, which is x. So it's 4 minus x.
Yeah, that's what I'm talking about.
That's what you were talking about. Oh, where it's minus x. I see. I thought you were just talking about a minus x as the radius. No, where you have to subtract. Okay, then you're right. R and h, what's h equal to? And there we go. Okay? Okay? Hey, we're cooking. 10. X equals 5. We're going around this line out here now.
Now that's what's it called, washer, right?
No,
No?
still a shell.
Why? Don't you have like a space between?
There is a space,
between every shell.
No,
but the key is your rectangle
it's parallel to the.
is, that's the key. You got it.
Because if you had, because your integral is only going from 0 to 4. If your integral is going from 0 to 5, then there wouldn't be that space. But because it's going from 0 to 4, it compensates.
It's true. Here's R, here's H. We're whipping around that line, x equals 5. We're going to use a shell. Volume, 2 pi. Integral, 0 to 4. R, this distance. What the heck is that distance? 5 minus x is correct because it's equal to 5 minus x. That's what the r is equal to, 5 minus x. And h, this height is x. That's it. Do-do-do-do-do. And number 11 is y equals 4.
So,
Go ahead.
Like you said, pretty much it doesn't matter if there's a hole there or not.
Doesn't matter. You know what? Same, you get the same integral. That's
Now,
basically
when you
it.
actually draw the triangles, are they infinite or that's as far as the triangle goes? It's only 4 to 4. It's only that point.
This triangle?
Bound by.
This triangle is going from 0 to 4. That's all.
That's it.
That's it.
Line y equals x goes
And
from-
how's the area gonna be with that hole? How's the area not gonna be the same? If you had a triangle up to 5, 5, for example,
Yeah.
how's the area gonna be the same? So that you'll-
It's not going to be the same volume, but the integral is going to be set up the same, except the limits of integration will be different, which will give you a different volume.
It's gonna go from 0 to 5.
Yeah, instead of 0 to 4.
Plug in a 5 for x instead of 4,
Ah, okay.
right?
Okay.
I just
Yes.
figured that out today.
Wow. Okay, whatever. Okay, we are going around y equals 4 this time. That's this line.
How do we know how high the triangle is? Does it say?
How high what goes?
Never mind.
Okay. Okay, now when I take this rectangle and I go around the line y equals 4, what will I generate? That will be a washer.
You couldn't use that.
Not if you're going to use this rectangle. If you use this rectangle, which is what I'm going to tell you to use, you must use washer
But
method.
there's no gap.
There is a gap. This is a gap right here.
Oh.
Okay?
If it was this way, it would be a
Oh, this is the
shell.
rectangle. It's the
Am
rectangle.
I correct?
You are correct. Okay, so we're going to use washers. Volume is going to be pi, 0 to 4. Big R squared minus little r squared. Now let's see. What the heck? Here's big R, and here's little r. Okay, as this thing gets whipped around that line, you got a big R. What's big R equal to?
X minus
4
R.
minus.
4.
4.
Yeah, 4 minus h.
Just plain 4. It's a constant 4. No matter where you are in this triangle, big R is going to be 4. But little r is not going to be a constant. What's little r going to be?
4 minus x.
4 minus, that's 4, minus this height here, which is equal to x.
Now, if you had a different y, it wasn't y equals x, you would have to find y, but since y is the same.
Yeah, yeah.
So here we just technically they would have been r minus y, but we changed it to x, right?
Yes,
Okay. That's
Yes.
just trying to get the.
yes, I believe what you said was right. This distance is equal to this minus this, the height above the x-axis, which is y, but we changed it to x.
Okay.
You're absolutely right.
That's what I was asking.
Yep. Any questions on this? How are we doing, okay? Are you cold? I'm sweating. I'm dying here. All right. 12 through 14. Here we go. You're given a function y equals cosine. You're going to set the integral that gives the length of the curve, surface area when revolved around the x-axis, and the surface area when revolved around the y-axis. Okay, let's do it. Y equals cosine x from 0 to pi. Okay. This is y equals cosine. Okay. Length of the curve is the integral from 0 to pi. Square root of 1 plus the derivative. Okay, here, let me give you the formula, I'm sorry. A to b, 1 plus the derivative squared dx. That's the formula for arc length.
Is it for everything or just?
Yeah, that's for everything. 0 to pi, 1 plus the derivative negative sine squared, which would be a sine squared, dx. That's the answer right there.
Wait, negative sine squared, what's negative sine squared?
The derivative of cosine is negative sine, but you're squaring it. Okay? Now, if you're going to whip this thing around the x-axis, it's around the x-axis. I wouldn't be surprised if everything canceled out, but that's all right. We're going to set up the integral about the x-axis. 2 pi, 0 to pi, RL is the formula. That's the formula.
This is for surface area?
Surface area about the x-axis. So what do we have? 2 pi, 0 to pi, r. Now, if this is going around the x-axis, that's r. As this goes whipping around the x-axis, what's r equal to? Cosine x is correct. Very nice. It's equal to cosine x. It's equal to the height above the x-axis, which is y, but everything is in terms of x, so y is the cosine of x. L, what's L? That's an element of the arc length. That's the 1 plus sine squared.
Is that number 13 that you're doing?
Yeah.
This is number 13. Now, interestingly enough, the arc length one, we cannot do that integral, and we will never be able to do that integral in this course. 13, however, which looks more complicated, is an integral we can do, and we will do in the next chapter, because we have the cosine out here.
We're just setting it up?
Yeah, all you're doing is setting it up.
So, for 12, technically, to get the answer, you would have to find the integral of 1 plus sine squared x, right?
The square root of 1
But
plus
we're not
sine
able
squared.
to do that.
You're not able to do that.
Okay.
Nope.
Is 1 full period on a cosine, is that pi or 2 pi?
Say that again.
Is a period
2 pi.
2 pi?
2 pi. Yep. You have to complete this cycle up to here again.
That's why I was like,
Yeah. And 14, if you're going to take this guy around the y-axis this way, it's going to be 2 pi, 0 to pi, r. Now what's r this time if you're going to go around the y-axis? That's r, okay? And what's that equal to? What's the distance from the y-axis? What is it?
X.
X, just plain x.
oh
Okay?
yeah, that's right.
And then you have the same piece of arc length, which is 1 plus sine squared.
Is it pretty much always x, unless it's like a different
Yeah,
way?
yeah, it is. When you go around the y-axis, this thing is always x here. And when you go around the x-axis, this is always your function here. Okay, that's your function. I mean, it could, yeah, we don't do any other stranger problems. Obviously, you could make some problems up where that wouldn't be the case. But the problems that we do about the x-axis or y-axis, that's what we're going to have.
So it's the function, which is, in this case, it's cosine.
Yep. All right, any questions on that? Yeah.
In the shell formula, there's a 2 pi up front, right?
Yes. 2 pi RH. Did I forget it or something?
No.
Oh, okay. Okay, 15 through 17. We got a spring. Work done by a spring. Here we go. Okay, it says a 12-pound force. Now what you're going to use, Hooke's law, 12-pound force stretches a spring 4 feet beyond its natural length. You use this information to solve for K. That's called the spring constant. Okay? This enables you to solve for K, that initial piece of information. K then is equal to 3. Okay? Now you're going to use K to find the work done. You find the work done in the spring by integrating, here, let me give you the formula, the force, which is Kx dx.
So is this still for 8, for 6, 5, 15? No.
This is 15 through 17. This is work done by a spring.
So that's like 16.
Yeah, 15 is Find K, that's what we just did there. 16 is find the integral that gives the work in stretching an additional 2 feet. Now, the addition, this is where you got to be, this is where these are a little bit tricky. We put the 12-pound weight on there, and now it's stretched 4 feet beyond its natural length. Okay? Now, we want to find the work done in stretching at an additional 4 feet. So it's going from 4 feet beyond to 6 feet beyond. So you have to do an integral from 4 to 6. That's what you have to do there. Okay? It's already 4 feet beyond. We want to stretch it an additional 2 feet, which will make it 6 feet beyond. We're going to go from 4 to 6 of K3x. Okay? That would be the integral that gives the work done in moving at that additional 2 feet.
So that's it, right?
That's it right there. And I don't believe I even have you do this one. Find the integral, yeah. So that's that.
So, for the example, if we mess up 13, which, just didn't think about it,
What?
will we be, will
15 you mean?
could we get half credit?
Yes. Yes. I will give you half credit. Yes, that's a promise that I will keep. Maybe. No, I will keep that. And now, 7. No, I will do it.
Wouldn't be surprised.
After removing the weight and allowing the spring to return to its natural length, find the integral that gives it work in stretching it 4 feet beyond its natural length. Now the integral is what? 0 to 4. These problems should not be a problem. These spring problems should be pretty simple. Okay?
So you don't even have us answering them?
I don't believe so. I believe that's it. Just set them up.
That was like last.
Yeah. I think that's all I have you do. The integrals are real simple, even if I did, but
Yeah.
I don't believe I do. And then 18 through 20, see, 20 I do have you find the fluid force here. Okay. 18 through 20. Okay, a 3 by 5, 5 by 3 rectangles placed in meeting with density 64 pounds per cubic foot. Okay. Find the force if it has an horizontal orientation at a depth of 5 feet. So, we're taking this with its horizontal orientation 5 feet below the top. We want the force on this object. Well, the force is not a calculus problem here. The force is equal to the density times the area times the depth. Okay? So it's the density times the area, which is 3 by 5, times the depth, which is equal to 5. Please note, you've got so many pounds per cubic foot here, then you've got feet, cubic feet, cancel cubic feet. Your answer is in pounds, which is what it should be in. So you end up with 64 times 3 times 5 times 5. 192 times 25. 192 times 25 is 4,800, I believe. If somebody has that done out, that would be nice, but I believe that's what it is. Somebody have it?
You're right.
Is it right? I still have it. I still have it. They look like I've lost it all, but I still have it. All right, that's 18. Now, 19 is an integral problem, although you could figure out how to do it without an integral. But suppose we're going to take the rectangle and now flip it, so instead of a horizontal orientation, it's got a vertical one. Okay, but the top edge is going to be 5 here. So here's what we got. Top of the water, 5 feet, 3 feet, okay? And this is at a depth, 0 feet. Oh, shoot. Okay, sorry. Sorry. My bad. I thought it was below the surface, but it's not. Okay, it's right here. Yeah, it's right at the surface here. Okay, this is your 5 feet. It's 5 foot side. This is your 3 foot side. Okay, this is what we have. It's got a vertical orientation now, this way. Now, we could do this two ways. One way to do this is without calculus, just by using your brain. Okay? So, if you were to take this and flip it right around the midpoint line, the midline right here, at 1.5 feet. Okay, so right now you got this rectangle, and you were to go this way with it. You're at 1.5 foot depth. The fluid force on that object would be equal to density, 1.5 feet, times the area of this thing, that's 1.5 there, and the area is going to be 15. So somebody do this out for me. I want to do this.
So why is it a 1.5 feet?
I get that it's in the middle, but what was
Yeah,
the
Problem
because
that needs to be in the middle.
it doesn't. I want you to do the integral, but I'm saying you don't even have to use the integral if you use your brains and flip it right around the midpoint. I'm going to use this to verify our integral. Okay, we're going to do this with an integral right now, and we should get the same answer as we get when we get here. So what is this?
Is it 1.5?
It's 1.5 times 15.
It's 1440.
1440? Thank you. Okay, 1440. That's the force on it. Let's do it with an integral, and we should get the same answer. Okay, here we go. Okay, with an integral, this is what you do. The force is equal to density, the integral from -3 to 0. Okay, -3 to 0. What do? Take the length of this rectangle. What's the length of this rectangle? 5. It's a constant, 5. That won't always be the case, but it's a constant 5. We did a problem the other day where you had a triangle where it wasn't a constant. Okay, you had to find the function y in terms of x and do that. Okay, that's equal to 5, and it's dy. And a depth of a negative y. I should have that. Okay, so 5, the depth is negative y. Okay, this 5 times a delta y gives you the area of this rectangle. What we're doing is summing up all those little forces on each of those rectangular strips, get a Riemann sum, get this integral. So this is what you have. Length, here's the general formula. Density, length of the rectangle in terms of y, the depth of the rectangle, negative y, dy. Okay?
So it's always in y.
Always in y. These problems are always in y. Let's do the integral, and let's verify that we get the same thing we had before. 64 times 5, I can take that out front, and I can take a negative out front. I have the integral of y dy, which is y squared over 2. Okay. Take this out, I get 32 times 5 is 160. Okay. Substitute in 0 to get 0. Substitute in -3 squared, you get 9. I get 160, a negative, times a -9. You get 1,440 pounds, which is exactly what we got without the integral. Okay? Now, does that mean you can always do these problems without an integral? No, it doesn't mean that, because if you had some other shape here, like a triangular region or something else we did, you would have to use an integral, because the fluid force is not the same on each point as you go down, okay? It changes. And the last one is find the force. There it is, 1440. Okay? Go ahead.
With that equation again,
See that
the
again?
row made it be length times what?
It's length in terms of y, length as a function of y.
Oh, okay.
That's what that is. That's the length as a function of y.
So if it wasn't y, to say, like y squared, that was.
Well, it's possible that you had something else, another function that defined that. It is possible. We're not going to get fancy with it. All we're going to have are straight lines or these constants.
What's negative y?
Negative y is the depth.
So, but then that problem is at 0. No.
One of the points is 0. It goes from -3 up to 0. That's correct.
Okay.
Yeah. Gus?
How'd you get the negative 160 times 0 minus 9?
This here?
Yeah.
Here's what I did. I took the 2 into 64 32 times. 32 times 5 is a -160. That's that -32 times 5. And then I put a 0 in here to get 0. I put a -3 in here to get the 9.
Oh, okay.
Yeah.
Why would you have to have it negative if it's already doing, go from 0 to -3?
Well, you got to be careful here because let's suppose you're at -2 here. What is that depth? At -2, your depth is 2 feet below the surface. So that's why you got to take the opposite of y. Y is -2, but you got to take its opposite to get a positive number there. And that's why this comes out to be a positive 1440, which is what it should come out to be. Okay?
Lab time?
All right, lab time here. I'm going to pass it. Oh, wait. Now, let's see if we... What? Hold on. What? What happened?
Oh, okay, never mind.
Okay.
That wasn't close.
Let me see.
Stop recording.